So hello everyone, it's Preetham Naikabi of Civil Department. Table of content: the influence of soil texture, environmental conditions of frozen soil, infiltration. Introduction: several processes occur simultaneously in a freezing soil, such as the phase of change of water with associated with latent heat flux, capillary gravitational flow, conduction of heat through the solid and liquid soil constituents, and the increase in matrix potential of frozen soil, resulting in redistribution of unfrozen water. Given the complex interactions of these processes, it is hard to predict the soil properties and environmental parameters. Affects frozen soil infiltration capacity. Laboratory and field testing would be demanding in the view of many possible values of process parameters, further complicated by the difficulty of measuring ice and unfrozen water contents in soils. The gain of the experimental studies is therefore mostly qualitative rather than quantitative understanding, despite providing useful measurements and insights. In this study, we use an existing single-domain numerical code to stimulate the freezing and thawing of variably saturated frozen soil columns in combination with infiltration of melt and rainwater. First, we assess whether the numerical code, which has previously been tested on freezing soil column experiments, could satisfactorily reproduce the full freeze thaw temperature cycle of a laboratory soil column experiment as well as the infiltration pattern into the frozen soil. Subsequently, we performed a series of numerical 1D tests simulations to investigate controlling factors on infiltration capacities of frozen soil, such as initial saturation, temperature, boundary conditions, and soil parameters. These results gave insight into the theoretical link between soil freezing and infiltration reduction, and the role of soil and environmental parameters play herein. The focus lies on the soil matrix flow, with the texture ranging from coarse to very fine, examined, and environmental conditions are chosen to encompass a wide range of possible field situations. Methods. First one, numerical model. In this study, we employed the semi-empirical version of numerical model that is described in detail by Sturop et al. It is one-dimensional water and heat transport model that includes the phase changes between the water and ice. We chose the semi-empirical version as it requires the least amount of parameters to stimulate freezing. The energy exchange body between the soil and snow or atmosphere was simplified by a fixed temperature boundary at the top. Experimental validation. The numerical model had previously been tested on 3 experimental data sets of freezing soil columns. To the test ability of the model to stimulate the thermodynamics thawing process as well, we compared the results of the model to full freeze thaw cycle experiment by Wong et al., in which the soil temperature was measured at different depths in the experimental. A 20 centimeter column with a silt soil at initial temperature of 1 degree Celsius was periodically frozen and thawed from the top. The side walls were insulated, while the bottom temperature was kept at a constant temperature of 1 degree Celsius. Freezing and thawing periods each lasted 24 hours, with a temperature of -5 and +5 degrees Celsius imposed on top of the soil column, which was repeated until a total of 6 days. The gain size fractions of these soils were reported in the original study, but not the water retention parameters and hydraulic conductivity. We therefore use the Rosetta pedo transfer function. So this is the diagram. Figure 1. Soil texture classification triangle. The dark gray areas are the soils simulated in the study, with the numbers referring the soil numbers in table 1. The larger red lines distinguish between the coarse and intermediate and very fine soils. The inorganic layer is placed in the area commonly classified as silty clay loam, because the organic matter layer are very similar water retention capacity compared to the soil type. Interpretation of the reference to color in the figure legend. The reader is referred to the web version of this article. All combinations of conditions in table 2 were tested of each soil type except for input water temperature. Water input temperature was initially varied in the simulations, but during testing we found it was non-noticeable effect. To limit computational time, we therefore only tested water input temperatures for soils 2, 3, 4, 5, and 6. So this is the table 2. Ice saturation. It is apparent that soils with intermediate textures had the highest ice saturation after freezing phase when looking at all cases. Combined in box plots, the concerned medians were upper quartiles and outer layers. These were the only soils which have cases with over 25% of the entire column saturated with ice. In comparison, the coarse soils, soil 1 and 2, never had more than 14% ice saturation of the column. With very fine textured soil, soil 7 8, we observed the lowest medians of ice saturation 0 and 3% respectively. Nevertheless, these soils had outer layer cases in which ice saturation exceeded 15%. Extreme cases. The appendix displays the cross tabulations of each and every variable combination and the frequency of cases, or 75% of infiltration reduction due to freezing. The highest number of cases was for most soils associated with low boundary thawing temperatures, especially at 0 degrees Celsius. This underscores the importance of thawing and the opposing process of infiltration, water freezing in situ with its effect of subsequent infiltration. Infiltration water freezes readily in still frozen soil because the available pore space has less metric pressure. Conclusion. Comparison with experimental data suggested the model is capable of simulating infiltration into frozen soil. Numerical simulation of higher number of synthetic test cases provided insight into the freezing, thawing, and infiltration process of various soil types during the different boundary conditions. Intermediate soil textures had the highest ice saturation and after the freezing phase compared to the coarse and fine soil, and therefore the strongest reduction in infiltration capacity due to freezing. Coarse soils were hardly affected, but very fine soils at some extent depending on specific conditions. Soil porosity facilitated soil cooling and thereby led to increased chances of infiltrating water freezing in situ, while high porosity slowed down soil cooling. The results of this study are based on numerical simulation and therefore provide theoretical insight into the freezing and infiltration dynamics of homogeneous one-dimensional soil column. The simulations provide a framework for further experimental work to validate or classify our findings. This study also provides insight into the intricate and complicated physics of frozen soil infiltration with many tripping points and process steering in different directions. A drawback of our approach in the lack of structural soil exchange during freezing and the absence of preferential flow. The current reality is that the little information exists to be able to predict a change in hydraulic properties due to freeze-thaw cycles. Thank you.